I'm going to be talking about using transistors during embedded development. So I'm trying to come at it from the angle of, okay, my output pin on my microcontroller, my project needs a little more oomph to accomplish what I am wanting to do. So what should I use to do that? Looking at transistors. In conclusion, all right, so I'm going to start with what the findings are, and then we're going to go as far into the why as you guys want to go. First off, if you're doing low voltage, BJTs come out on top. I was actually doing a project where I was trying to use a 1.5 volt pager motor, and trying to switch that with a FET was just exceedingly challenging because I didn't want to put a different circuit on there for doing current limiting and doing a more complicated thing than I needed to. It was battery operated, one battery. But when I used a BJT, worked like a charm. The BJT only needed 1.6 volts.
What does BJT stand for?
Bipolar junction transistor. Good question. The transistors fall into three different categories in general right now. BJTs, which are the oldest and most mature technology. We'll touch on NPN versus PNP. The P's are usually the little black TO92 triangular things that most of the time when you're looking at one of those, you're looking at a BJT if it's a transistor. Again, the BJTs excel at low voltage use.
Why did you pick 3 instead of 3.3?
Because the trick is that MOSFETs have a threshold voltage, and the voltage you need to turn a MOSFET on varies with the design and layout of that MOSFET. But once you go below 3 volts, you really have to start studying the data sheets and the usage conditions to figure out if you can use a FET or a particular FET or not. Where with a BJT, at above 3 volts you're fine. But once you get down below 3 volts, if you have a BJT, it will work. You don't have to finesse the data sheet and be scratching your head. So you know if you grab an NPN BJT to switch a 2 volt source or a 1 volt source or a 3 volt source or a 4 volt source, it's going to work. If it's a FET, you have to go to the data sheet, because if you're doing 3.3 volts, even if it's a logic FET, that doesn't mean it'll work at 3.3 volts. So you have to actually go in and study the charts in the data sheet. So as a gray hair saver, hair puller, if you're going to be using below 3 volts or below 5 volts, a BJT is safe. That kind of falls apart once you get above 500 milliamps. I'll go into that more in this. If you're in the 500 milliamp and up range, you're right at the cusp of a BJT being acceptable. And one of the reasons is that a BJT generally has a fixed voltage drop across it, 0.1 volt to 0.2 volts. So at, say, 0.2 volts at 500 milliamps, you're dissipating a watt. And that's a lot of heat for a little TO92 chip. Where with a MOSFET, your voltage drop across a MOSFET at half an amp would be virtually 0. So if you're doing 200 milliamps, 300 milliamps, that's probably going to be safe to use a BJT. You're going to be close. It may run a little warm, but it's still going to work. But once you hit 500 milliamps, it's not worth the headache. Use a FET. High current, definitely use a FET. If you're wanting to switch 20, 30, 50 amps, there are MOSFETs out there that can do it. If you use the proper wiring, proper board layout, proper driving, we'll hit on some of that.
FET.
Oh, I'm sorry, field effect transistor, MOSFETs. When I say FET, I mean MOSFET, metal oxide field effect transistor. And there's like 6 different kinds, but we're really talking about enhancement mode. I'm only going to touch on one. And mostly I use NFETs. BJTs and FETs, interestingly enough, both have N versus P semiconductor types. We'll touch on that in just a little bit. If you're wanting to do high-speed switching, above 10 kilohertz, 10 kilohertz, 50 kilohertz, 200 kilohertz, or megahertz, the FETs don't mind switching those frequencies at all, but layout gets much more important and you want to use a FET driver. If you're doing something...
You want to explain what is high speed?
Above 10 kilohertz.
Okay, and I understand what kilohertz is, but what am I switching that's that high speed?
If you're transmitting high-speed video over long lines, you may be buffering it. It's something
Okay.
like that, and that may be 100 megahertz that you're buffering. It may be DC to DC power converters or step-down converters that you may be chopping at 400 kilohertz. You may be chopping them at 2 megahertz. So if you're doing high-speed magnetic stuff with DC to DC converters, you're most definitely going to be using FETs and probably not using BJTs.
Nothing that I would ever do, do I care about that?
No, when you care about this is if you're trying to do a very high-speed pulse width modulation, like say you're trying to pulse width modulate something at 10 kilohertz for some reason, that's why I throw a driver out there. It's duck soup. You can make an Arduino do it. You can make a Pi do it. But getting an output pin to push the current in and out of the gate of a MOSFET by itself, you start getting sloppy, and then your power dissipation goes up in the MOSFET because you're spending a lot of time in the transition region instead of the conduction region. But a driver will take those rise times and put them in a sub-microsecond range, so that all of your dissipation is in your conduction region for the MOSFETs just itself. And for the insane, want to work in the high-power physics, doing pulse demonstration of magnetic stuff, IGBTs are the insulated gate bipolar junction transistors, which are a little bit like BJTs and a little bit like MOSFETs. That's where those thrive. If you know somebody who says, well, I'd like to switch this 3,000 volt source at 200 amps at 250 kilohertz, you want IGBTs. That's what they live at.
So that's next week's class.
Yeah. I searched at DigiKey just today while I was going through my notes here. The highest single dissipation IGBT that you can get at DigiKey is 2,300 watts. That's not switching power, that's dissipation in the switching element. I want to say that was like 3,000 volts at like, I don't know, 60 amps or 100 amps.
So the burst power has got to be even higher than that.
Unbelievable.
Oh, yes.
So Doc had to use that for his 1.21 gigawatts on his switch
Yes,
capacity.
he was most definitely using IGBTs.
Gigawatts.
The funny thing about IGBTs is they have a fixed voltage drop across them. So if you're running 20 amps and it's got a 2-volt drop across it, you're getting 40 watts of dissipation across it. But it doesn't care if you're switching 2,000 volts at 20 amps. It's still just 20 watts dissipation. Where MOSFETs, their on resistance varies with the voltage. If you want to have a high voltage standoff, it takes a structure that creates a higher on resistance. So an IGBT, it's very easy for them to make high voltage structures, where MOSFET, it's a lot harder to make a high voltage structure. But Moore's Law is marching away steadily, and I think that the next 24 or 36 months are going to be very exciting in MOSFETs, because we're crossing a threshold to make them applicable to utility line voltage, wall outlet voltage. Yes.
How fast can IGBT switch?
I've seen hundreds of kilohertz. I don't know what the upper limit is. Most of the stuff I've seen was handling high power things, but I know that they've got impulse ratings on them, so to me that implies megahertz level. But a quick trip to Wikipedia, I'm sure, can educate you more on IGBTs, but I've got a couple more slides on IGBTs in a little bit. Here's Brian's question. Why do I care? That typically we're wanting to add a transistor because we're wanting higher current. Say I'm wanting to switch on a relay that has a 500 milliamp coil or 1 amp coil, or I'm wanting to switch a higher voltage. One of the interesting things, if you're trying to do like piezo positioning using piezo crystal actuators, they may need 1,000 volts, but only at a milliamp or 2. There's some MOSFETs that fit that great, that you drive directly from your controller. Some of the bottom things, lower down the list, inverter signal, very handy that if you have a signal coming in that the phase is wrong, or if you've got a signal that's coming out that you don't want to change the phase up for another reason, one transistor gives you inversion. You can translate voltage levels. You've got a 3.3 volt CPU, but you need to be talking to a 12 volt bus. One transistor will fix that problem for you. The same thing if you have a chip that only has digital outputs. Pulse width modulation is actually a digital output, no matter what anybody says. You can use one transistor and a couple of parts to actually convert that to a genuine linear analog output voltage. Easy to do, one transistor and 2 passives. Again, BJTs, really good for low power. They also, interestingly, that includes high voltage. As long as you're doing low power, high voltage, you're still getting high voltage. MOSFETs really excel at high current because of the three, MOSFETs are the reigning champion of low voltage drop across the switching element. They can have microvolts or lower of loss across the switching element, where the BJTs have at least 100 or 200 millivolts, and the IGBTs will have at least 1.3 volts. Most of them have 2 point something volts across them, and there's just nothing you can do about that.
Shane, the MOSFETs, are they the ones where the gate is very sensitive?
Yes, and
You can blow that out if you don't watch or something?
You can't blow that out. I think that's a little overblown. I can't remember.
Okay.
I can't remember the last time I've blown up a FET, but I have blown up microcontrollers from handling them without proper ESD. So I know that it can be done. Stepping into how do you use a BJT. This is an NPN BJT, and I'll hit NPN and PNP in a few slides down. One of the things is the base resistor here, R1, is always needed because you actually have here between the resistor and ground, that acts just like a diode, like a silicon diode.
Which one of those wires is the base?
Oh, the base is the one connected to the base is in the middle, collector on top, emitter on the bottom. The emitter is the one that looks like it's doing something. It's got some parts to it. And the way I remember NPN versus PNP, this is not pointing in. So NPN, not pointing in. And the way this works,
And a FET is not my thing.
the way this works is as soon as your control voltage gets above 0.6, you start getting current conduction through R1 to the base, and then the transistor multiplies that by the transistor gain. So let's see, that's probably 5 volts. I don't know how much current that's driving there, but it lets you put very low strain on your transistor. This is actually from a SparkFun tutorial on transistors, which is a great tutorial. They've got some really cool stuff on SparkFun. Here's how you do something similar with a MOSFET. I actually pulled this off of something I'm working with Chip on, so it'll look familiar to
It's
Chip.
in my church too.
Pardon?
It's in my church too.
Oh, okay. You'll see this again later. The same sort of thing, but notice here where the BJT only needed one resistor, minimum. You had to have that gate resistor. Here you have to have two. This is driving the gate of the MOSFET, and the 100 ohm resistor does two things. One, that if you're driving that capacitor with no limiting resistor, you're going to be fatiguing your output transistors.
What capacitor?
This is an insulated gate, so notice it doesn't touch there. It's like a capacitor. It really is a capacitor. It uses the charge on the capacitor to induce conduction between the drain on the top and the source on the bottom, but it requires no gate current. So the only current flowing through here is to charge that capacitor. Once you turn this on, you can hold it on forever, and the only current flowing will really be what you're using to keep this 100K pull down from pulling the gate down. The reason you have that gate pull down is that capacitance collects voltage. So stray voltage could accumulate on that gate until it turned on and randomly turn on your relay or whatever it is.
How'd you pick 100K as a value?
That's a reasonably aggressive value. You'll see anything from 100K to a meg to 2 meg. The really high ones are generally used when you're using a really weak driver. And you really just need something to keep static from being able to pull it down. And the 100 ohms I've thrown in there, that's also a very arbitrary number. That a gate resistor is recommended because the FET actually has a lead, a pin on the gate, and the inductance of that pin combined with the capacitance of the gate make a little RC circuit that can cause ringing, that can actually shove the gate out of its safe voltage range. And having a gate resistor on there helps damp that and keep the ringing from being able to take your gate out of the safety range. So it's really just for the protection of the MOSFET as much as it is for the protection of the pin driving it.
Shane, are these the type of components that have enhance and non-enhancement modes?
Yes, and I've never used non-enhanced. The only thing I've ever used is enhanced. So that I think most of the ones that when you start looking at those are for small signal, special things, buffers, mirror
The
amplifiers.
non-enhanced versions, you mean?
Yes.
Okay.
Yeah, I think those are more specialized analog applications, stuff that I don't have
Sure.
much experience with. Let's see. Here we go. This is how you invert a signal with a BJT. It looks complicated, but it's not. Well, it looks more complicated than a switch, but it's not much more. In essence, your output here is pulled up to whatever voltage that you want. So it could be that you're driving this with 3 volts from a Raspberry Pi, and this could be a 5-volt output that's going to another circuit, or a 12-volt output. But you really only need this signal to go far enough above the gate voltage, the base voltage of 0.6 volts. So you could use 1 volt on the input and use this to convert it to whatever output level that you wanted. Got a cool circuit that's a little fancier using a MOSFET. Now this is a very clever circuit because this one is actually bidirectional. It goes both ways. Let me explain how it works. It's actually 2 different circuits. You'll notice the little diode symbol here that you should always see on power MOSFETs. It's one of my pet peeves is when people leave it off, because even if it's not on the drawing, it's still in the package, whether they tell you or not. And so many people have gotten bit by it because if you hook the transistor up backwards, it looks like it turned on and you can't turn it off, when really what it's doing is behaving like a diode. So what happens here is you'll be translating one way or the other. Generally, you won't be going both ways at the same time because you wouldn't have 2 outputs trying to talk to each other or 2 inputs saying they're listening to nothing. So whichever direction you want to go, let's say you're transmitting 5 volts from here. Well, when it's a 0 and there's nothing happening here, this is all off and this is pulled up to your low voltage. So you're pulled up to say 3.3 volts on your Pi. But when you drive this up to 5 volts, I'm sorry, I've got that backwards. When you drive this high, nothing happens here because this FET's being driven backwards. So this is high, nothing's happening over here, this is pulled up, so this is high. But when you pull this down, you're not actually using the FET, you're using the body transistor, the body diode. So you're pulling down here, and it's pulling this to 0.6 volts. And by the same token, if you, I thought I had it plugged in. Let's see if we can race through here and beat it. But if you're going the other way, and say you have a low signal, let's look again. So how does that work?
It's a level converter.
Yes, it's a level converter. What was I going to say? When you drive, that's it. When you drive this one high, when you drive this high, the FET gate is tied to the voltage. So the FET is always on from this perspective. So yeah, you drive this low, you pull that down, that's right. But when you drive this high, there's nothing to conduct through here, so this pulls up to the high voltage. The one thing that I thought would have been better about this is if they reversed it, because this is driving the FET with the low voltage as opposed to the FET's going to enhance better if you drive it with the high voltage. And if you flip it around, the lowest that this is going to be able to pull the low voltage down is the 0.6 volts, so you're going to have less voltage margin, where if you're using higher voltage logic over here, by definition, you're going to have higher margins. So I feel like it should be flipped and go the other way with the FET, but the circuit would work the same way. It would just shift the voltage favor over to driving the FET with a high voltage and using the 0.6 volt minimum 0 voltage on the high voltage side rather than low voltage side. Yes, sir.
And isn't this the level translator that works with I2C?
This is the one that works with I2C, that it actually came from an app note that Phillips recommended for bidirectional I2C, which SparkFun has actually turned into a little board that they sell.
Also.
Okay, I didn't see the Adafruit board.
And does Pololu have one? I
There's
bought
a million
some of
of
them, I'm
them.
trying to think which one I've got, SparkFun or Pololu.
They all, a lot of them do.
I've got one that actually has 4 of them on it, and it actually has a little power supply chip on there too.
Oh, yeah.
That'll regulate the voltage.
Yeah.
Is it not?
I don't think those are hot.
Try plugging it into the,
There's a socket right there.
Ah,
Yes, you do.
right
Put
next
your
to the
electric
cable,
bill.
that would have made more sense.
Is it?
Maybe I filled the power supply. was after the level shifter? Wait, it's coming back, I think.
Other than the fun of making one, why would I want to make one if I could spend a couple dollars and buy the?
Well, understanding how it works.
Understanding how it
That's
works.
what tonight is about.
Yeah, and it's also at different levels. If you're just prototyping it, the buy a board falls, there's a very narrow range for buy the board. If you're roughing it and you've got a choice between I'm going to finish it today or tomorrow, or I'm going to pay $20 for FedEx to bring me one tomorrow, versus I can rummage something up in my parts bin and use, you know, loose pieces that I've got that I paid 15 cents for.
I actually made some out of 2N7000.
Okay, I'm not familiar with that one. Yay,
So that's a general purpose MOSFET in a TO92.
Yeah, it's an exception to your rule. It's a simple MOSFET in a TO92.
Yeah, I've got the best TO92 MOSFETs that you could buy from DigiKey, but they were only rated for 3 amps and still had 750 milliohms of. But I wanted the best I could get in a TO92 package, so I've got them. And here's what I was talking about on converting a digital signal to pulse width modulation to a real analog signal. What happens here is when you put a pulse width modulated signal across the resistor, the capacitor smooths out the pulse width modulated waveform and turns it into a voltage that the NPN here actually amplifies and turns into a steady state current. And this is one of the applications where a BJT really beats a MOSFET. And the reason is if you're working in the non-saturation region, say, this looks like it's going to be used in saturated anyway, that they just want to be able to turn it on smoothly, this transition. But say you're wanting to do this where you're actually wanting to control it. You can change this voltage and double the current through the transistor. And this transistor will, according to the beta, give you about twice the current. But with a MOSFET, you're actually floating up and down the gate sensitivity curve. So doubling voltage on the gate is not going to give you a corresponding linear scaling of the current. Yes, Carl?
Well, I think it's good to point out that a BJT is a current amplifier and a FET is a voltage amplifier.
Yes. These are the BJTs are current mode devices, and the field effect transistors are voltage mode devices, but the FETs don't really multiply the voltage. There's a resistance that corresponds to that voltage, and you get whatever current you want through it based on it. But the voltage
That's the same
control.
thing with a BJT too, right?
No, not really. On a BJT, that as long as you're not exceeding your pull down, it immediately clamps down to 100 volts or 200 volts across the VCE, across the collector and emitter here. But if you're running it in an open mode, you can do linear control that you can say, I'm going to put 5 milliamps through.
Depends on where you are in the curve, right?
If you're staying on this side of the saturation curve,
Yeah.
then if you put in 3 milliamps versus 6 milliamps, you get twice as much current from a BJT. But you can't say for a MOSFET, oh, I'm going to go from 2 volts to 4 volts, and I'm going to get double the current. I can guarantee you're not going to get double the current. Yes?
The other thing that you pointed out is that despite being a voltage device, while it's charging that gate capacitor, the FET is sucking current. It's
Yes.
consuming current
Yeah.
while it's getting switched on.
I'm going to touch on that for just a little bit for the FETs. But the FETs depend on that voltage getting them down into a low current range. If you're operating in a linear mode, the FET has all the disadvantages of the BJT and none of the advantages. Yes, Brian?
All right, so in this circuit, when I send my signal for LEDX, the LED is going to just slowly.
Yes, and this is, I think, from Evil Mad Scientist Labs. I've got a list of references at the end, and they use this in a Halloween pumpkin that they're doing Cylon lights on. And what they found is that the lights were just, when they were doing the pulse width modulation, they were just coming on too coarsely, and they were still seeing flickering. This took all the flickering out and converted into smooth transitions, and again, junk box parts. Any other questions on this one? let's see. This is the advanced level, so don't let this bother you if it doesn't make any sense. This one, I only thought it was neat because it's actually, this and this are the same circuit, but using a BJT NPN for the switching element versus an NFET. This is one of the coolest circuits in all electronics in my mind. Because what happens is let's say your gate resistor, let's pull it out here and you're driving it with your Raspberry Pi, you're driving it with your Arduino. So that's where gate signal's coming from. But what's neat is this transistor sits here and does nothing, whether that's on or off, until the current through this resistor is large enough that the drop across the resistor reaches 0.6 volts. At 0.6 volts, this transistor starts to turn on and it steals drive current from the FET. So it doesn't matter how hard you're driving RG, it will steal it until this stabilizes at 0.6 volts. So you're going to drive through that diode, or whatever your load would be, you're going to drive 0.6 volts divided by that resistor. So if you have a 0.6 ohm resistor, you're going to drive 1 amp. So it doesn't matter what your load is, as long as it's, you could have a 1/10 of an ohm resistor, which should be drawing, from the 12 volt supply, 120 amps. But use a 0.6 ohm resistor there and it'll drive at 1 amp. So what I like it for is for driving high power LEDs, or for driving an external load that you want to say, I want a 10 amp load, but you can put a sizable resistor, which will have substantial heat dissipation. You're probably going to have a 5 watt resistor, 10 watt resistor, but you can be sure that if you short your output within reason, if you short your output hard enough, no, it should still work because this is still in the ground eternally, it will limit your current to the 600 millivolts divided by that resistance.
Is the gate on the MOSFET there being?
No, it's a nice slow linear thing, because what happens is the NPN here comes on soft, like let's say it's at 5.5 volts. It's thinking about turning on, and then okay, it creeps up to 0.6 volts. Okay, now I'm going to turn on and start stealing a little current. Well, if you've got a really high load on there and the current is ramping, every time the voltage across the sense resistor goes up a little more, the NPN pulls a little harder until it pulls too hard and cuts it off and the current drops. And it's like, oh wait, and then it cuts off less, gives up a little bit, the gate comes back up. So what happens is it quickly pulls the gate down to, asymptotically approaches the nice smooth level for constant current. So you get
MOSFETs don't like having the gates floating in the middle?
darn good point.
It's not in saturation or something?
What you're thinking of is a CMOS totem pole output, which definitely does not like to be left floating or being somewhere in the middle, because you get conduction into top and bottom and you get the shorts. This is related, but not the same thing. What happens is the circuits we were talking about before when we were switching with the MOSFET, we're using that low RDS of a MOSFET. Right here, we're losing the benefit of that very low RDS, because what we're doing is we're shoving the MOSFET back up into the linear region and giving it the resistance we need to draw 1 amp across that load. So all the power in that 1 amp, so let's say 12 volts, 1 amp, you're drawing 12 watts. If your load's only consuming 2, that other 10 watts is going to your FET. So your FET that normally could switch that load all day long with no trouble at an amp or 10 amps or even 20 amps. But if you put it into a linear mode, you're asking to dissipate 10 watts of heat. So you better be heat sinked or it's going to start smoking soon. That makes sense to most. The fun part. How do we kill a transistor? You'll learn quickly. Just because it doesn't look hot when you lick your fingers and touch it doesn't mean that it's not hot. But I've burnt the little serial numbers of the FET on my fingertip before. The easiest way, and I'm going to talk about substitutions in a minute, but the easiest way is to do over voltage or over current. Easier to do with low power BJTs. If you forget to use a base resistor on a BJT, I've seen them left out of some circuits where there's enough line impedance so they're being fed by a high resistance coil and you don't realize that it's in there, and then you go to modify it. Underdriving the gate of a FET is a great way to kill it. I've actually overheated some in what I thought were really simple circuits because I was trying to drive a non-logic gate-sensitive FET with a logic level signal, so I was only half turning the FET on at any time.
Why does that crap it out?
Because what happens is the FETs fall into a whole range of categories of how sensitive their gate voltages are. Generally, the limit is don't go above 15 or 20 volts. But some may take 10 volts to turn on, some may only take 5 volts, some may only take 3.3 or 2.5. I was using one that needed 10, and I was driving it with 5. So it was turning it halfway on. So it should have had an on resistance, I think the case I'm thinking of is of less than 50 milliohms. And I was only drawing a couple of amps. So it should have had virtually zero heat dissipation, but it was getting hot. And it's because it was actually turning on and having, you know, an ohm of dissipation, an ohm of resistance. So if I'm sending 2 amps through it, that's 2 amps squared. 2 is squared is 4 times 1, 4 watts. So it's sitting there, free air dissipating 4 watts, so it's going to heat up pretty quickly versus it should have been dissipating less than, I think, less than a tenth of a watt. Let's see. Here we go. This is the overshoot. I tried to put these in the order of, okay, now we'll start getting into more minutia. This is what the BJT NPN looks like. Current drive devices that they do need base drive. They are available in high current devices, but the beta, which is the multiplication factor of that, when you send, you know, say the MOSFET, the BJT has a gain of 100. You send 1 milliamp in the base. Out of the emitter, you get 100. You get 1 milliamp plus beta times that. So if it's got a gain of 100, you get 101 milliamps, drawing the other 100 milliamps from the collector. But if you go up to something that can handle, say, 5 amps, you may go from having a beta of 100 down to having a beta of 20. So when you want to push 5 amps and a beta of 20, that means you're going to need 100 amps of drive current. So you're past what you, pardon?
100 milliamps.
Sorry, 100 milliamps. You're going to need 100 milliamps of base drive current. So you're past what you can do with a micro. There are Darlington devices that actually use one transistor to drive the next transistor, and they have a couple of glitches to them. They can let you drive very high currents with very low voltages, very low drive currents, but you do need a higher drive voltage, where you can drive a regular NPN with any voltage above 0.6 volts. With a Darlington, you need at least 1.4. So if you just stick into a Darlington that was working, almost working with an NPN, that's not a guarantee it's going to work. And the Darlington drop across it between the collector and emitter is a minimum of about 0.85 volts, just because of the way the structure is. So you're going to lose that much voltage versus you may have only had 0.1 or 0.2 volts across an NPN. The other thing I don't like about Darlingtons is they can turn off very slowly, particularly if you've drilled them in saturation. So you can think you're doing a nice clean pulse width modulation and they'll turn on quick, but they have a slow tail to turn off. So you're actually skewing your pulse width modulation. MOSFETs, there's a drain on top. That's the most positive portion of the circuit, or the transistor circuit. Anyway, the source is on the bottom, has the gate. The gate is capacitive and voltage-driven devices. There are many devices on the market that can get you very low on resistances. Some can even go below a milliohm. But it also depends what voltage range you're looking at. Again, Moore's law is moving in our favor. But still, if you're wanting a 200 or 400 volt device, you're not going to find anything with an on resistance of less than 5 or 6 milliohms.
That diagram has the internal workings of the MOSFET shorted.
With a diode.
Not the diode, the MOSFET. The internal workings of that MOSFET are shorted.
You're right. No, that symbol is an error. I did not catch that. No, that bar there should not be there.
That's right. Yeah.
Point to that again.
The topmost bar. Are you messing with me, bro? That bar should not be there. That should be open. But I think I've got another circuit there.
You did have another one earlier, that was
Yeah,
correct.
it's just a little drawing here.
Also, and this is just a question, but like in one of your things, the symbol for the diode was a Schottky symbol as opposed to whatever.
They vary. Some have the symbol internal like this. Some have it shown external. The ones I don't like the most don't have it at all, and that's one of the things I'm actually struggling with the latest Art of Electronics.
Yeah.
They've actually switched to a completely new symbol, and they leave out the diode. which I'm really struggling comfortable with.
But
You're saying the
if
shot-
everybody knows the diode's there, why do you care if it shows it?
Because if it's not on the diagram, you can forget it's there. So you're like, instead of thinking, why am I seeing 0.6 volts across this MOSFET? If you look at your schematic and you see a big diode there, that's a, hey,
I
0.6
agree.
volts, that's a diode voltage. I think it's very helpful.
Especially if you're building H-bridges where those diodes are used.
Yes. IGBTs, the love child of the BJT and MOSFET. That combines the low saturation voltage of the BJTs with the FET drive, actually invented by Jay Balaga, 1977 when he's at GE, who is currently a professor here at NC State. So the guy who invented the IGBT, his office is right across the way. But I actually read about him when he was receiving some IEEE accolade when I was in graduate school in material science, across the hall from his lab, and I thought, that guy looks a lot like the guy across the hall. And looked it up, and I went, I mean, I get goosebumps thinking about it now. I went across, I felt like I was meeting Mick Jagger. I mean, this was 20 years ago, and it was already a billion-dollar industry that he invented there. But they do have some great points. They handle high voltages with the plomb that they get from the BJTs. But it's a good side and a bad side. They have that fixed voltage drop across them of about 2 point something, so it doesn't matter how many amps you're running through it. You're going to have to dissipate X amps times that voltage drop that you don't have with MOSFET. But they'll also, again, you could get them up into thousands of volts and thousands of amps range.
How do they cool something like that?
Big heat sinks. Big heat sinks. And I know that some of the things that they do also depends on duty cycles, so they won't be running at 100% duty cycle, but yeah, they have massive heat sinks on. And here's the symbol. It's kind of funny that when you look at the equivalent circuit, you can see that it has what looks a little like a Darlington transistor pair inside of them, along with a MOSFET on the front end, and the symbol looks like a combination of MOSFET and the BJT symbol. That they have gate drive requirements similar to a MOSFET. Most of the people I've read about using them successfully recommend knowing your stuff when you're doing the gate drive or using the gate driver. I've never used them personally because every time I've gone into starting to use them, I keep coming back to, no, I would rather have lower passive dissipation in my device with a lower voltage drop across it, so I end up coming back to a MOSFET. Yes, sir.
Mostly switching or mostly analog?
I'm not very familiar with their use in
Because
analog.
I'm just wondering, what about solenoid?